My goal for this video is to help you understand how to do an induction proof with a power of matrix question. And this question is from the 2023 A-level further math paper. So let's have a look. We're going to prove that this matrix to the nth power is equal to, notice that the n becomes right here. It's true for all natural number n. So remember the induction proof. First, we will have to do the base case. Actually, step 0. If you are doing a proof, write down P at first. You just feel good, seriously. First though, induction proof, so I should say by induction. Well, why did we choose induction? Here's the deal. Usually, well, most of the time, when we have a statement involving like all integers or all natural numbers, then you can try to use inductions. For integers, it might be trickier because you have to consider the positive side, the positive integers, and also the negative side, the negative integers. You just get two parts. But this right here is just positive integers, pretty much. So by induction, firstly, we are going to check the base case. So I'm going to specify that this is the base case. And for natural numbers, I'm going to start with n is equal to 1. If you have n is equal to 0, I don't think that, well, that's a debate I'm not going to get into, but anyways. Base case n is equal to 1. It's the same as the official answer key, they start with 1. Put a 1 into here, then we can see that 1, 0, negative 2, 1 raised to the first power. Well, the first power doesn't matter, which is of course the same as 1, 0, negative 2. And if we are just multiplying the 1 right here. So it checks. Yes. Now, here is the IH part. This is the inductive hypothesis. So I will spell it out. Inductive hypothesis. Oh, hey, I can spell. Look. Inductive hypothesis. So what we are going to do is that assume the statement is true. The statement is true. So I will write down the claim or the statement. The claim sounds better. The claim is true for some value, but that's not use n anymore. Usually we like to pick another index or another variable. I'm going to say for n is equal to k. So what that means is that, right, that is we're saying we have 1, 0, negative 2, 1 raised to the kth power. This is equal to 1, 0, negative 2 times k and then 1. Right, so this is the assumption that we have. Now continue right here. Right, continue. Now what we have to do is we will have to check what will happen for n is equal to k plus 1. So we will put k plus 1 into this n. 1, 0, negative 2, 1, and then k plus 1. And hopefully we'll see that we will be able to put the k plus 1 into here. That means the statement, the claim is also true for k plus 1. So that means we can be done. Now, this is just like a rule of exponent. It's still the same with matrix. We can write this down as 1, 0, negative 2, 1 raised to the kth power, and then times 1, 0, negative 2, 1 raised to the first power. Then for this part, we can use the inductive hypothesis. This right here is equal to, and again, this is by inductive hypothesis. I'm going to kind of put this down. This is the same as that. 1, 0, negative 2, k, 1. Haha, very nice, huh? And then multiplying with 1, 0, negative 2, 1. Now, we just have to multiply this out. So remember, we do the dot product of a row and a column. So for the first entry, we do 1 times 1. So I will write down all the steps for you guys. 1 times 1 plus negative 2 times k times 0. And then continue, we do this times that for this entry. So 1 times negative 2. So the red times negative 2 and then plus negative 2k times 1. Okay, so perhaps I'll put a little parentheses. And then continue this times this. So it's 0 times 1 plus 1 times 0. That's nice. It's just 0. And then finally, this times that, the dot product. So this times this, 0 times negative 2 plus 1 times 1. Ladies and gentlemen, that's 0, that's just 1. That's 0. This is negative 2 minus 2k. So write this down. And then this is just 1. Are we done? Well, almost. Here is the final part. I'm going to write this down in this form. So I would like to factor out the negative 2. So this equals 1, 0, factoring out negative 2. And then we'll just have 1 plus k left. So can we write it as k plus 1? Sure thing. And then finally we have the 1. So from the inductive hypothesis, we get to move to the next step, meaning if that is true for k, it's also true for k plus 1, so we are done. Finally, put a proof box. Right? Put a box and shade it in because we're done with the proof. That's it. Haven't done an induction proof for a while, so hopefully this right here is helpful and all that good stuff.